Well, it is, right, exactly.
It's very crazy.
Right.
Yeah.
But I think quantum field theory kind of makes it make a little more sense, if that makes sense.
Welcome to the New Orleans Humanist Perspective, presented by the New Orleans Secular Humanist Association, following a few principles of humanism.
We're committed to the use of science and reason for understanding the universe and for solving human problems. We're skeptical of untested claims of knowledge, but we're open to new ideas.
We are concerned with securing justice and fairness in society and in ending intolerance and discrimination. We are committed to the total separation of religion and government.
We affirm humanism as a realistic alternative to the theologies of despair and the ideologies of violence. We reject the concept of an afterlife and believe in living a full and rewarding life here and now.
We value and respect each individual's right to judge and lead their lives according to their own position, as long as it's respectful of other people, living in a free society.
We hope you enjoy today's program and others in the weeks to follow.
Hello, welcome to the Humanist Perspective. My name is Jeffrey Brite. I have a really good topic for you tonight. Tonight we're going to be talking about what's up with physics. My guest tonight is visiting professor at Tulane, Nick Sparks. Hi, Nick Sparks.
Hey, how are you? Good to be here, Jeff. Thank you.
Yeah, thanks for coming. I met Nick just recently and found out that there's a theoretical physicist that understands this stuff, and I was hoping maybe he could explain it to me and the audience as well. So let's just jump right in.
Cool.
What I wanted to do is break down this into a couple different topics about what's current in physics, or at least the cutting edge of physics, and discuss, like, maybe you can break down each one of these topics for us and see if we can get down get an explanation that maybe a layman could understand that's not a physicist.
Sure.
So one thing that's been in the media a whole lot is about dark matter.
Right.
Can you explain dark matter? Maybe I'll give you
absolutely. So when we look at the total breakdown of mass energy in the universe, it turns out that 68% of that mass energy, E equals mc squared, energy and mass are the same kind of thing. 68% is called dark energy, and that's responsible for the expansion, the acceleration of the universe.
Right.
27% is going to be dark matter, what you're asking me about.
Right.
And we know about that based on violations of what is called Kepler's law, essentially how galaxies rotate.
Right.
And then only 5% of the remaining stuff is actually what we interact with on a day-to-day basis.
So is it fair to say that we only understand 5% of the universe?
That's very fair to say that we only understand 5%. Yeah.
So how do we know that we only know 5%? So how do you guys figure that out?
Right. So what's going on is science is data driven, and so what happens is again, we're basically off by 95% because a lot of the theory that we have written down doesn't agree with the data that we've actually found.
Of observed data.
That's correct. And so there has to be some kind of a missing mass or some kind of an energy that permeates the universe that actually allows for this expansion and for these galaxies to be rotating at the rate that they do.
So you're saying that if we use our Kepler's law and Newtonian physics, that and try to calculate what would happen in a galaxy, it would behave differently than what we observe.
And it does, absolutely.
Right.
That's right. So in other words, dark matter is sort of a fudge factor, if you will, that we introduce to try and get the correct observations that we're seeing.
Right.
And this is kind of an invitation to go back to the drawing board and fix our theories.
Right. So could it be that Kepler's laws are wrong and Newtonian physics is wrong? We just need to fix the numbers and then suddenly it all makes sense?
Well, seeing as Kepler's law has been so successful and Newtonian physics has been so successful, it seems doubtful that they're wrong. It seems a better candidate that dark matter is actually the correct culprit.
I see. And so do we have any ideas about what dark matter is?
Oh, there's plenty. So this is where theorists like myself and others come along. But some of the properties of dark matter, the reason why it's called dark is because it doesn't interact with light in the same way that regular matter does.
Right.
So clearly it has mass because it interacts gravitationally.
Right.
But when it interacts with light, it isn't giving the same radiation that regular matter would be giving.
Right. And now, if it's going to be a matter, in theory, we can interact with it?
In theory, that's right. And so one of the candidates for dark matter, some people have proposed that it's actually antimatter.
Okay.
But again, if that were to interact with matter, the rules of physics say that energy would be given off. So if you're familiar with Star Trek, for instance, of course, their engine is given by a matter-antimatter reactor. Right. And so as we know from Star Trek and from physics, when matter and antimatter react, they give off a lot of energy.
Right.
So if regular matter were to interact with dark matter, if it were really antimatter, we would be seeing radiation. There would be a signature left over from it.
So are you saying that just to get off of dark matter just for a second, are you saying antimatter is real?
Antimatter is absolutely real.
And are we confident that that's sci-fi?
This is totally verified. Absolutely.
Okay.
This is actually antimatter is an interesting topic because it's the first time that theory actually preceded experiment in detecting it.
Is that right?
That's right. So in 1927, Paul Dirac, a very famous physicist, interpreted negative energy solutions as being antimatter, and then in 1931 it was actually discovered that a positron existed, which is antimatter form of an electron.
Oh, very interesting. Very interesting. So you can have an antimatter atom and then
a particle of antimatter. So actually, as far as actual matter, in terms of like how an atom forms, an atom is made of electrons and protons and neutrons. In terms of antimatter, that actually hasn't been observed before, where it actually would form an atom.
Okay. All right. So that's the dark matter picture is that we have some matter. Where do we believe is it just that it would concentrate closer in the center of the galaxy or on the outside? Where would it be?
Yeah. So it's actually on the outside is what we kind of postulate, because at the very center of a galaxy, a lot of the times when you see these beautiful Hubble pictures, they're actually spiral galaxies, and at the center of galaxies, we believe, are black holes.
I see.
And so the actual dark matter would reside on the outside. Okay. And actually, as a matter of fact, one of the candidates for dark matter is actually something called a primordial black hole, meaning that there actually might be these weird microscopic black holes left over from the Big Bang that are actually out there, and that accounts for the missing mass.
I see. Okay. And all right, so so that was dark matter. Let's go into dark energy, which you said is the thing that's like pushing the universe apart.
That's right.
And how do we know that that's actually a thing?
That's right. So Edwin Hubble is a very famous astronomer who actually showed that galaxies actually are receding at an accelerating rate apart.
How did he figure that out?
This was actually all experimentally driven.
Okay.
So this is actually through looking at telescopes at the time. This was done in the 30s.
Right.
He was actually able to show that the farther away a galaxy was, the faster it was accelerating. This is called Hubble's law.
Okay.
And at any rate, what happens is the universe is accelerating. It's getting further and further apart. Now, that's not to say that 2 points are necessarily getting further apart. It's actually the space-time itself that is stretching almost like silly putty.
Yeah. So, we have to get into space-time, I think, to explain that. So what is space-time then?
Yeah, space-time is an interesting concept. And so this is a notion from Albert Einstein, but it basically says that we can't think of time and space as actually being separate entities. They actually have to be sort of put together. And the way that I like to kind of think of it, and maybe this might be a little bit naive, is almost kind of like silly putty, because to some extent there actually is an interaction between matter and energy that space-time can actually have. So you've seen the famous pictures of like space warping, or there are bends and things like that.
Sure.
That's how we kind of picture space-time. It's actually a setting where physics occurs.
So matter warps space, the space-time around it.
That's right. Matter tells space how to bend, and space tells matter how to move.
Right. Okay. And so it's this median, the space-time, that's actually stretching over time, right?
And this is all a result from the Big Bang. This is there's an epoch of acceleration, and it's actually caused by what we were discussing.
So why doesn't it slow down?
That's a really great question. So essentially what's going on is we might ask the question, what could slow it down?
Right. Well, gravity, you would think that gravity would slow it down over time.
Exactly. The natural candidate would be gravity. And so what we have to do is we have to look at essentially the relative strengths of each of those forces. So is gravity a stronger force than this dark energy?
Right.
And the answer so far is no.
Right. And so what are the candidates for dark energy then? What is that?
Yeah, so this is actually going to be a little bit technical, but what it is, it's actually a field that permeates space. This kind of gets into this notion of quantum field theory, which we might talk about a little bit later.
Yeah, I would love to talk about quantum field
theory. But it's actually like a residual energy that was actually left over from the Big Bang that actually spreads itself out all over the universe as it expands. To give you a good idea of what the expansion of the universe might look like, imagine that you have a balloon that you haven't blown up yet.
Right.
If you take a marker, like say a Sharpie marker, and you put dots all over that balloon,
right,
those dots might represent the galaxies or the matter that you see.
Sure.
When you blow up that balloon, you'll notice that the dots are actually getting further apart, right?
Right.
But the reason they're getting further apart is because the balloon itself is the thing that's expanding. That's right.
See. So that's an interesting.
And so the blowing up is kind of like the dark energy. You're sort of putting the dark energy into the balloon more or less, and that's what's blowing it up.
So I've heard one thing that was interesting about dark energy is that, and correct me if I'm wrong on this, but my understanding of the ideas about the early universes as it was from Big Bang started expansion, that there was this concept of inflation that expanded very rapidly.
Right.
Is that related to dark energy in any way?
It is. And I'm not an expert on explaining like that particular epoch, but you are correct. There actually is this period where it rapidly underwent expansion, and a lot of the physics is still being investigated as to what the cause of that is, what it means.
Right. So the Big Bang happened, then it expanded greatly, slowed down, it must have, and now it's expanding again.
That's right.
And so, those two phenomena could be related.
So it accelerated, but the acceleration slowed down, but it still is accelerating.
Okay.
That's right.
Okay. All right. Well, I think we covered dark energy. I hope that was dark matter and dark energy. I hope that was a good explanation for everybody at home. And we'll try to do better next time if we can. So one of the big news items in physics that came out in the last couple of years is about the Higgs boson. What is that?
Yeah, so what the Higgs boson is it's kind of like a small little bit of something called the Higgs field.
Okay.
So Higgs boson is like a particle. So if you imagine to some extent, if you have a bunch of these particles that are all scattered all around, that forms something called a field.
Okay.
And the idea is that a Higgs field is essentially what gives everything in the universe its mass.
Right.
When it interacts with this field, it acquires its mass. So think of it kind of like a fluid to some extent, and think of particles as being kind of like fish inside of this fluid.
Right.
The smaller fish that are more streamlined and easier to swim would have less mass than, say, the big fish that are kind of bulky and kind of can't get around as much. But anything that interacts with this field has mass, and that's what the Higgs field is. The Higgs boson is just a tiny little manifestation or a particle of that particular field.
So now how did that come about? As I understand, it was also theorized first and then discovered at the Large Hadron Collider.
That's right.
So how did they know that there must have been a Higgs boson and a Higgs field
in the first place?
Right. Yeah.
So that's a really cool question. So what happens is, if we go farther enough back in time, what happens is all of the laws of physics, or not laws, but rather forces of physics, are essentially manifestations of one force. And this is called like grand unification. It's sometimes what it's called. But one of the pieces of that puzzle actually needed was this Higgs field.
Okay.
So it's kind of like a missing puzzle piece to some extent.
Right. And that was discovered by
Peter Higgs.
Peter Higgs. Okay,
yeah,
so that's
why
they named it after him.
And several other people.
Right. And so they come up with this idea that there must be this Higgs field and this must be this Higgs boson, and we decided that we're going to go after it and try to see if we could detect it. Right?
Oh, sure, absolutely.
So can you describe the experiment that they did to try to detect it?
Yeah. So what's essentially going on is, whenever you hear about these particle colliders, you hear about the Large Hadron Collider at CERN in Geneva, Switzerland. Well, the idea is that what we're trying to do is create kind of an environment that is similar to the Big Bang. And so the idea is when you can get something in high enough energy, essentially what we do is there's a joke amongst particle physicists that says that if you want to know what a chicken is made of, you have to take another chicken and slam it into the chicken and see where all the feathers go, right? So it's a little bit of a macabre description, but to answer your question, at sufficiently high energies, these particles actually emerge from collisions of protons.
I see. So is that why it has to be so large? Is that they have to get them up at such high speeds?
Precisely. That's right.
I see. Well, okay, and so how important was the Higgs discovery then for physics?
It was a missing boson in kind of our particle zoo, as we like to call it. Right. So it's kind of like putting together a piece of a puzzle to some extent, and we found a missing piece.
Right.
So
that you knew had to be there. You knew the shape of it.
Well, it was definitely predicted, and for very good theoretical reasons, it was definitely there.
Right.
Now, what's interesting about that? I was actually a graduate student still when it was discovered. And I was discussing with Dr. Lev Kaplan at Tulane. I remember walking in his office. I said, "We discovered the Higgs. This is great. You know, we had 5 standard deviations worth of accuracy, which means it's extremely accurate." And he wasn't as bright-eyed as I was. And I said, "Well, you know, what gives? Why aren't you happy about this?" And he said, "Well, we knew that it existed, you know, and so like we just discovered something that we already thought existed. So there was not any real new physics that came out of it."
Right, it wasn't that exciting to her.
Well, I thought it was really cool.
It was very exciting to me at home.
I think it's cool. Yeah, I still think it's cool. But yeah.
So now just to dig into the experiment a little bit, as I understand it, the way that they detect these things is that they can't just collide a bunch of things together. Go look at it. Sometimes the Higgs doesn't show up. It's a statistical phenomena, right?
Oh, sure.
So when they have to do the experiment,
you have to just mine the heck out of a lot of data.
Right.
That's right.
So why can't they just, you know, if you were trying to do the chicken experiment where you send them together, okay. I'm sure we'd find all the parts afterwards, right?
Sure.
So why couldn't they find the Higgs after just one time?
It needed to be at a sufficiently high energy. I mean, to use the chicken analogy, maybe if you at low energy, if the chickens collide, maybe only a couple of feathers go off. But if you really get it going, well, then you got a mess on your hands.
Right.
And we were going after the mess that would produce the Higgs boson.
Right. So how many times did they? So as I understand, there's that it's at 5 sigma.
5 sigma.
What does that mean?
Yeah. So what's going on is when we talk about sigma, what we're talking about is something called a standard deviation. What does that mean?
Yeah. What does that mean?
What that means is it's essentially a measure of a spread of data. So to give you an idea, if I were going to be looking at the heights of people walking by as I'm watching people walk by on the sidewalk, within one standard deviation or one sigma, 68% of the people would fall between plus or minus 1 standard deviation.
Okay.
95% would fall between 2 standard deviations. 99.7% would fall within 3.
Right.
So I'll leave it up.
You like your bell curve.
The bell-shaped curve. That's right. And so what happens is if the average person is 5'6" and let's say that the standard deviation is 2 inches, well, you can kind of do the math from there. Right. So 5 sigma is pretty significant.
I see. Well, that's really interesting. So that's okay. So we got caught up to speed on the Higgs. I hope we did a good job on that. The next thing I think that's been in the media most recently, a big discovery is we actually detected gravitational waves.
Right, at LIGO,
right, which is
in Livingston, Louisiana, which is our backwoods. Yeah, really exciting.
So what is a gravitational wave? And then the next question is, how do they detect it?
Sure. Yeah, so what a gravitational wave is essentially is anytime you have matter or energy, it radiates. It kind of gives off a little signal, no different than some of the radio waves that we use to tune our radios, right? And so what happens is essentially what the gravitational waves that we discovered at LIGO happened is 2 black holes actually. Black holes, by the way, are very massive. Actually were interacting with each other, and because of all that energy in their interaction, they radiated some of that energy away. And what we detected is something
in the form of a wave.
Oh yeah, absolutely. All radiation.
And this is a wave on space-time, then?
It is. That's right. So that's a really good question. So when we think about waves, we think of water waves or we think of sound waves. And what's kind of interesting about those is that they have a medium that they go through.
Right.
Now, gravitational waves are actually waves in space-time.
Right.
So that's really weird. So basically what's going on is going back to the silly putty argument. What happens is that stuff can kind of like, wave around a little bit.
Right, compress,
it stretches
right.
and compresses,
Right.
kind of like a slinky, like a 3D slinky.
Right.
And that's essentially what the gravitational wave is in.
And so that's what they detected. They detected two black holes.
Oh, yeah. That's right.
Were they revolving around each other?
That's right. And so they were interacting rotationally.
Right.
And the idea is that by working backwards, we actually were able to determine that based on the signature of the waves that arrived.
And how far away was these black holes that they detected?
Many light years. Yeah.
Okay.
Yeah.
And so we detected that. How did we detect that?
So that's a
because we didn't feel it on Earth, right?
Oh, we're right now as we speak, and for the people watching, what's going on is there are gravitational waves going through our body all the time, right?
Right.
In fact, when I wave my hand, I'm actually creating gravitational waves, right? But these are so minuscule that you would
below
never
human
detect
detection.
them. That's right.
It's like seismic activity. We don't detect.
We don't detect it exactly.
Right.
It's just below the threshold of our own detection through our five senses. That's right. Now, how did they detect these gravitational waves from these black holes? Well, what happened is there was an experiment done with an apparatus that's called an interferometer.
What is that?
An interferometer is essentially something that looks almost like a giant L shape.
Okay.
And what happens is, as this wave comes by, it causes some kind of a distortion in one of these legs of this L and in the other one. Right. And what happens is you can measure that difference.
Okay. Okay, and so that's what, and that's it.
And that's what they did.
How big is the experiment?
Yeah, so the one in Livingston, and I encourage people to go check that out. They have a really great museum there. Is actually on the order of a couple of kilometers.
Okay.
So we're talking a very massive size of an arm for an interferometer.
And do you know the story on how Louisiana got it? Because we're not usually considered a destination for scientific experiments. So.
I unfortunately don't.
Just curious if you knew that.
I unfortunately don't. There's another one in Washington State.
Right.
And we actually corroborated the data that we got there and here, and to see if we actually detected a gravitational wave.
Excellent. Now, as I was saying, they're building a third one. I forget where they're.
Okay. Yeah.
Something I read. All right. Well, that's fascinating, and also that's like one of the last pieces of like Einstein's theory of relativity that's been experimentally verified.
That's right.
Because he predicted this, right?
Yes, in 1915, actually.
So, how did he figure out that? Is it just through the idea that that the median being space time and using the formulas of gravity, that if these things were happening, we would experience it here? Is that all that is?
That's right. So
formulas?
Einstein deduced this from what are called the field equations, and the idea is that what happens is on one side of the equation you have mass. And on the other one, you have how space reacts to that mass.
Right.
Now, if you do some mathematical approximations, you can actually get a wave equation to come out of this.
Right.
And this is how Einstein was able to deduce this.
That's really interesting. It's neat to see, like, someone who's just sitting down thinking about how the universe must work, and then being experimentally verified.
It's a truly beautiful theory too.
Right.
It really is. It's quite simple actually, but there's a little bit of a learning curve. Maybe. Yeah.
All right, simple for some, I guess.
Simple for some. Certainly not me when I was first learning it, but it is beautiful.
Right. Okay. Well, I think that catches us up on a lot of the topics. Why don't we see if we can jump into some of the more theoretical topics? Maybe that's it. You hear scientists talk a lot about the theory of everything, or the unifying theory of the universe.
Right.
What is that to a layman?
Right. Well, so theories of everything are essentially they can mean lots of things, but the most popular one is this. Trying to unify the very, very small, i.e. quantum mechanics, with the very, very large, which is gravity, general relativity. Right.
So why don't we maybe, if you can give us a brief explanation of what quantum mechanics is, and see if we don't lose everybody.
Yeah, sure. So quantum mechanics is the physics of the very, very small.
Right. And how small are we talking?
We're talking about probably a billionth of a meter or something like that, or a billionth of a yard if you're a football fan.
Okay.
So very, very small. And the idea is that at that very, very small level, we can no longer really speak in terms of definite objects, right? So if I had a baseball here, we would say, well, here's the baseball. But if it were a quantum baseball, it could be in several places at once, depending on how we measure it.
Right.
So quantum mechanics is like a statistical theory of nature.
Right.
And it is the theory of nature. I mean, this is what has given us the best results and made the best predictions of physics so far.
I see. So it's a mathematical, understanding. One of my favorite quotes on quantum mechanics comes from Feynman, who said, "If you think you understand quantum mechanics, you don't understand quantum mechanics." So I guess
I am guilty of that. Yes. There you go.
So you can only wrap your head around it from a mathematical concept, but from a common sense point of view, it simply will not make any sense.
That's right. Feynman also said that he talked about shutting up and calculating, right? So quantum mechanics is sometimes where we have to not really know what's going on, but we still have a framework in which we can actually make predictions.
So what would be an example of just something that's counterintuitive to a human experience, but that just is commonly understood in quantum mechanics to be happening?
Yeah, sure. So there are lots of different cases, but one of my favorite is this idea of something called the Schrodinger Cat Experiment.
All right. So I think a lot of people heard of
Schrodinger's cat.
Explain that.
Sure. So what Schrodinger's cat is a thought experiment where what happens is you have a cat inside of a box.
Right.
And depending on when you look inside this to see this cat, the cat could be alive or dead. There happens to be a poison particle that decays at some random kind of event, right?
Right.
So what happens is the rules of quantum mechanics tell us that this cat, before we actually observe it, could be both dead and alive simultaneously, right?
Right.
So at the quantum level, you might see light switches that are on and off simultaneously, but at the macroscopic world where we live, things are definite.
Right. So, so is the cat alive or dead? Are you saying that it's actually both? Is that what you're saying?
I'm saying it's both.
Right.
That's right. Which seems nonsensical.
Right.
But this is backed up by very hard science.